Hey, welcome back. I know you're here for the ants program or for the continuation of the ants program. But due to lack of time, I wasn't able to prepare it for this week, so we'll have to defer it to the next week. In the meantime, let's look at some reaction diffusion algorithms and see what they look like. Hey Ravi.
Hey.
So I wasn't able to complete anything on that ants or at least continue with it.
Sure.
And the reason for that is I haven't had 3 hours of continuous time where I could actually sit and work through the problems that we've been having.
Sure.
I think the last time we left it at the ants were able to drop their pheromones, search and seek for food and all of those things. So we'll still need some more time to actually prepare for it. And so I'm hoping that by next week I have enough time to work through it.
Correct.
In the meantime, let's look at some reaction diffusion algorithm. And it's a very simple thing. We've done things of this sort in the past,
right,
where very simple equations give rise to very complex reactions, very complex very complex patterns being generated and all.
Yeah.
And I think those were, even the Mandelbrot set, the chaos, and then the game of life, all of those were like simple rules but giving complex patterns, complex phenomenon and all of those things. So let's have a look at it. I have this website open and everything. All right. So this is a very famous computer developer. His name is Carl Sims, and in this page he describes the reaction. Basically this is the reaction diffusion tutorial, and what we'll do now is we'll look at his algorithm and we'll implement it in JavaScript and see how it
Sure.
we can see what it looks like.
Right.
Or we'll just put in the initial conditions that he's talking about and see if we can get the same output as such.
Very cool.
All right. So it's a simulation between two virtual chemicals, and let's talk about what this reaction diffusion is. All right. Let's take two chemicals. In this case, the most simplest of chemicals, just water. Let's say you have like a tub of water and you take a drop of food coloring. So eventually, and if you put like a drop of food coloring in this water, you'll see that getting diffused into the water. Eventually what will happen is that this chemical, which is this food coloring, will eventually diffuse and it will vanish, but in the process it will create these very beautiful patterns, and all of these are actually dependent on the initial conditions that you are putting in.
Right.
All right. So we'll look at what these initial conditions are and everything. All right. So I think this site by itself describes it very beautifully. There is nothing that we can add to it that will make it much more clearer as to what this diffusion is and all of those things. So let's just jump straight to it and look at the algorithm itself. All right. So the algorithm states that you have two chemicals. You have two chemicals A and B. So at the next slice of time, or basically when we do that request animation frame and the next slice comes, the next value would be the previous value plus this is the dA means these are the diffusion rates of A and B. These are actually preset or predetermined. Now these are constants.
Right.
All right. Diffusion of A and B followed by Laplacian functions. Okay, so over here these are 2D Laplacian functions. That's what he's talking about.
Right.
Which gives the difference between the average of the nearby grid and everything. Let's look at this. What he's talking about over here. So this thing, right?
Right.
We are going to do it in a grid, right? So if you take, let's say, this center point over here, Laplacian means you sum up all of the neighboring grids, the surrounding grids based on the values that are given over here. The center weight is -1, adjacent neighbor is 0.2, and diagonals is 0.05. That's what he says that Laplacian A is. Laplacian B is also something something very similar, but it adds the B portion of the chemical.
Correct.
All right. So minus AB square and the A chemical and the B chemical, followed by the feed rate. So again, one more constant. So the feed rate. So there are two constants that are very important here: the feed rate and the kill rate. So the feed rate is how fast it is like, put into the thing, and kill rate is how fast it diffuses or is removed by the other chemical. And that is actually very beautifully described over here. So how fast is this, how fast you can add it to this, and then how fast it is removed by the other chemical. So that's what it means. And when you actually put this for certain starting conditions, it will give rise to these very beautiful patterns. There are some patterns that have been described over here. So for example, there is one very famous one, I think it's called mitosis, and it sort of looks like exactly like cell division and some such.
Wow.
So we'll implement this and see how it goes.
Super.
All right.
Sounds good.
All right, let's get coding. I already have an index.html file that will house my canvas. The canvas is rendered on the screen like so. Going back to the code, you will see that I already have the JavaScript file declared. Let's have a look at the JavaScript file. In the JavaScript file, I have some global variables, which are essentially the width, the height, and the context on which we will be drawing this. The context is initialized like so. I get the canvas that is declared on the HTML file, and then I declare the context, and I also initialize the width and the height of the canvas element. And then I also have this reaction diffusion function that will be our loop function. This will be our loop function. All right. Let's start by creating the requisite variables. I'm going to declare a constant here called grid size, which will be of size 200. This grid will be rendered on this canvas that I'm declaring over here. The canvas will also have the image and the pixel data declared against it. I'm also going to declare the diffusion, the feed rate, and the kill rate values as prescribed by the website Carl Sims. Next, I'm going to declare the reaction canvas as a document element. Once I have done that, I'm going to set the reaction canvas's size to the grid size. Now the reaction canvas, from the reaction canvas, I'm also extracting the context, and from the context we get the image data. This will give us the pixels that are contained within that canvas. Let's take a look at the Carl Sims website once again to see what the grid should be initialized with. It says that the grid is initialized with A equal to 1 and B equal to 0, and a small area is seeded with B equal to 1. All right. So the grid has both these chemicals with chemical A as 1 value and chemical B as 0 value, but a small area is seeded with B equal to 1. So let's code that. All right. So let's initialize the current grid and the next grid. I am declaring them as empty arrays for now. We'll have an outer loop first, and in the outer loop, we'll initialize the grid contents themselves as empty arrays so that they become two-dimensional arrays. Now in the inner loop is where we will assign the values 1 and 0 to the A and B values of the grid. All right. Now if you look at the title clip that I'm displaying on the screen, you will see that I'm setting the values of A and B exactly as prescribed by the algorithm on the Carl Sims website. Next, I also need to declare, or I also need to initialize a small portion of the grid itself with B value as 1. So that's what I'm doing right now. All right. So our next job is to convert this formula or this algorithm into our code. So let's do that. I'll start by creating the loops necessary to perform this reaction. Our loops, if you notice, start from 1 index and they end at grid size -1. You will see why that is in due course. Now I'll get the A and the B values from the current grid. This is the value of the A chemical and the value of the B chemical. And now I'll have to say what will be the value of these chemicals in the next iteration, which means I'll have to assign them to the next grid. So I'm essentially transcribing what is given in the Carl Sims website onto this function over here. You'll also notice that I'm writing a function over here called Laplacian A. All right. And when I'm calculating the B values, I'm also using a function over here called Laplacian B. Both of these functions we'll define in just a little while. All right. So we'll just let this complete. All right. The kill rate plus feed rate multiplied by B. Now, once I have this, I also have to ensure that the values of A and B do not exceed values between 0 and 1, and that is what I'm doing over here. If it exceeds 1, then it remains as 1. If it becomes less than 0, then we just assign it as 0. This way we constrain them between values of 0 and 1. There are better ways of doing this. This is the way I'm doing it. Let's define the Laplacian functions. In the tutorial, it says the Laplacian is performed with a 3x3 convolution with center weight as -1, adjacent neighbors as 0.2, and diagonals at 0.05. What this means is that within the grid, you take every pixel or every element of the grid. The center is weighted -1, which means you multiply either the A or the B values with -1. The adjacent values, which have to be weighted as 0.5, and the diagonals are 0.05. All right. With that in mind, let's define the Laplacian functions in code. We'll simply call our functions Laplacian A and Laplacian B. Both these functions look very similar. So once we declare Laplacian A, we'll simply copy over its values to Laplacian B. We'll declare a variable called sum, and as prescribed by the website, we'll have the center weight as -1, the left, right, top and bottom values at 0.2, and the top left, top right, bottom left and bottom right at 0.05. What we are doing over here is simply getting the values of the adjacent grid values, adjacent grid cells, and adding them up to the sum value. And all we have to do now is return the sum value. All right, so let's do that. Let's return the sum value right now. And once we have the Laplacian A, we just simply copy it over, and we do the same for Laplacian B. Except for Laplacian B, we use the B values of the grid. All right, so remember how our grid loops was starting from 1 and it was ending at grid size -1. The reason for that is because we need to perform these Laplacian operations with neighboring cells. All right, now that we have completed the reaction diffusion algorithm itself, we need a way for it to be rendered on the screen. And that can be easily achieved by simply converting the A and the B values into a component color. All right, and that can be easily done like so. All right, let's start by creating our grid loop. Now remember, we will have to convert our double dimensional grid into a single dimensional positional argument. And that can be done by getting its pixel value by converting x plus y into the grid size multiplied by 4. Each pixel essentially has 4 values in it, which will be the red, green, blue, and the alpha values. All right. So what I'm doing over here is I'm getting the grids A and B values. I'm converting it into a color. I'm checking for the color limits itself. Color can only be values between 0 and 255, which is what I'm doing over here. And once I have that, all I have to do is now set the pixel values. All right. Each 4 pixel data values consists of 1 pixel, which is what I'm doing over there. Once I have done that, I will put the pixel data back into the context. And the context, which is represented by the reaction canvas, is once again drawn onto the main canvas itself. All right, so let's have a look at the result, shall we? When I refresh the screen, you will see that nothing happens. The block that we set the B value as 1 remains just as it is, and nothing happens, no reaction happens. And the reason for that is we're not doing any swapping with the current and the next grid. All right. So what should happen is that every frame of this animation, the next grid and the current grid should swap values. So let's write that swap function, shall we? Or let's just write the swapping code over here. Temp is equal to current grid. The current grid becomes the next grid, and then the next grid becomes temp or the current grid. All right. So after we do that, let's look at what the reaction looks like, and you will see that something does start to happen. Now, what happens is, now you will notice that this grid is actually very small, or the image that is being formed is very small. And the reason for that is because we have declared the grid size as only 200, which means that out of this 800 by 800 canvas, we are utilizing only about 200 pixels of the image as it is. Now this can be easily solved with with a function that is available in context. All right, and I can just say context.scale, and I can say now if the grid size is 200 and if the canvas size is 800 by 800, how much do you think that the scaling factor should be? You're right, it should be 4. All right, so I'll just say scale the X and the Y by 4 times, and then you will see that the image will be centered and it will also be a lot bigger than what we had seen earlier. All right, now let's look at the results with Ravi. All right, Ravi, let's look at the results, shall we? Yeah?
Sure, yeah.
Okay. All right, let's see. Yeah, there you go. So that basically creates that pattern that he is talking about.
Right.
What we'll do is we'll speed through this.
Okay.
I mean, and we'll see how the reaction goes.
Right.
And we'll see if we get the same value as what he predicts that we'll get.
Yes.
Okay. All right. So let's just speed through this. Two, one. That was good, right? That looked good.
So good.
I think you need to speak into the mic. Yeah. Yeah, that looks so good, right? Okay, Ravi, let's look at that mitosis reaction that we talked about, right? So I think the feed rate is 0.028 and the kill rate is 0.062. So let's look at what that looks like. There you go. That looks exactly like mitosis, by the way. Right?
Oh, there is the division happening.
Yeah, that's the division. Each blob or each globule sort of becomes into two, and it creates this very beautiful pattern, right? It's just changing a little bit of the initial conditions. We're able to create beautiful reactions, right?
Very nice.
Yeah. I'm in the mood to change this into a color model. So basically introduce some color into it and let's see what it looks like if this was a little bit psychedelic. I already have the code prepared over here. Let me just uncomment this, which basically introduces color into this whole thing. And let me comment this out. And let's see. So this is the mitosis reaction in color. So that looks beautiful, right? Yeah. I mean, it still keeps dividing, and you can see, I mean, those initial conditions of the feed rate and the kill rate taking shape.
Wonderful.
Right? Yeah.
Wonderful.
Yeah. So that's all I had for this. So that's all I had to show for this week. Let me switch back cameras over here. All right. So that's all I had to show for this week.
Sure.
We'll continue with ants definitely the next week. I'm really hoping I find
time to
to complete the ant behavior.
Sounds good.
Yeah. So keep tuned. I mean, how do you say that?
Yeah. Come back next week.
Watch us
finish the ant simulation.
All right. Thank you so much.
Ciao.
Ciao.